Welcome back to Chapter 1.2, Expectations, Variance, and Covariance as Geometry, Part 4 of 9. In Part 3, we collected scaling, bilinearity, and symmetry. Now we combine them into the fourth rule, the variance of a sum, which is the equation Maya's whole problem rides on. The headline, the variance of a sum, is not just the sum of variances. It carries a cross term, twice the covariance, and that term is where diversification comes from. We close with a classic trap. Uncorrelated does not mean independent. Combine the three rules and you get the fourth. The one Maya's whole problem rides on. The variance of x plus y equals the variance of x plus the variance of y plus 2 times the covariance of x and y. That deserves a slow look. The variance of a sum is not just the sum of variances. There is a cross term, 2 times the covariance, and it can be positive, negative, or 0. If the two variables tend to move together, risk compounds. If they tend to move oppositely, risk cancels. Derive it once. Write the variance of x plus y as the expected squared deviation, push the expectation inside using linearity, and expand the square into a deviation in x squared, a deviation in y squared, and a cross product. Those three pieces are exactly the variance of x, the variance of y, and 2 times the covariance. The general weighted version, which is what a portfolio needs, follows from scaling plus bilinearity. The variance of x plus by is a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance. When does the cross term vanish? If the covariance of x and y is 0, we call x and y uncorrelated, and only then does variance add cleanly. The variance of x plus y equals the variance of x plus the variance of y. Independence implies uncorrelatedness. Independent variables have the expected product equal to the product of expectations, which kills the covariance. But the reverse is the classic failure mode. Uncorrelated does not imply independent. Take x symmetric about 0 and let y equal x squared. They are tightly linked. Y is a deterministic function of x. Yet the covariance of x and x squared is 0 when the distribution is symmetric, because covariance only senses linear co-movement. Covariance is blind to curved relationships. Hold on to that. It is exactly the limitation that linear regression inherits in week 2. To summarize part 4, the variance of a sum is the sum of variances plus twice the covariance. That cross term, which can compound or cancel risk, is the entire seat of diversification. When assets move together, risk piles up, and when they move oppositely, it cancels. The weighted version is what a real portfolio uses. Finally, uncorrelated means the covariance is 0, but it does not mean independent because covariance only senses straight lines. The symmetric x and x squared example are dependent yet uncorrelated. In part 5, we put all of this to work on Maya's 2-asset budget, running 3 scenarios and watching her portfolio's risk drop below its safest ingredient.